On a cold, windless night, far from the noise of cities and their restless lights, you look up and see something so simple that it seems beyond question. Stars that glitter, shiver, and wink at you from the darkness, as though some invisible hand were gently disturbing the fabric of the sky. And it is in that ordinary childhood moment, when someone first asks, "Why do they twinkle?" that you step unknowingly into a story thousands of years long. A story of priests and poets, navigators and philosophers, experimenters with glass lenses and quiet mathematicians tracing invisible currents of air and light. Imagine first a time with no names for constellations, long before astronomy was a profession or a science, when small groups of humans huddled around fires on the African savannah, and the night was both a ceiling and a question. Their eyes, unspoiled by artificial light, would have drunk in a sky so dense with stars that the Milky Way itself resembled a river of crushed ice, and among those countless points, the unsteady ones, their quivering living quality, could not possibly have felt like mere decoration. When those early watchers saw a star brighten, dim, and flash with hints of colour, they had no language for refraction or turbulence, but they had language for spirits, for ancestors, for gods who might be signalling approval or warning. And it is easy to picture an elder gesturing upward, tracing with calloused fingers the sharp, vibrating rays surrounding a bright star near the horizon, saying that such a restless light must belong to a soul not yet at peace. In that world, where the wind in the grass and the whisper of the fire seemed to answer back, twinkling was not a problem to be solved, but a message to be interpreted. As bands of humans travelled north and east into Mesopotamia, the night sky became not only a canvas for myth, but a ledger of power and fate, and in clay tablets baked under the Babylonian sun, we find some of the oldest systematic records of how stars behave, scratched in cuneiform by temple scribes whose duty was to read the sky as a sacred text. These scribes noticed that certain stars, those close to the rising sun, or hovering low over the dusty horizon, flickered more intensely, occasionally flashing red or green, and they folded such observations into an immense apparatus of omens catalogued in texts like Enuma Anu Enlil, where the bright, agitated stars were linked to upheavals, famines, or victories in war. In that world, the heavens were not far away. They touched the tops of ziggurats, those stepped mountains of brick where priest astronomers spent long hours at night, watching, waiting, and marking down on wax-coated boards whether a star was steady like a royal decree or wavering like the mind of a foreign king, and though their concern was divination, they inadvertently produced one of the first long-term records of atmospheric optics, because every note about a fluttering or unquiet star was really, from our perspective, a measurement of how the moving air of ancient Mesopotamia disturbed its light. From the floodplains of the Tigris and Euphrates, you leap to the valley of the Nile, where the priests of Egypt waited each year for Sirius to rise heliacally just before dawn, an event that heralded the coming inundation. To them, Sirius was a goddess, Sopdet, and her appearance was both a calendar and a promise. Yet anyone who has watched a bright star near the horizon shining through a thick slice of atmosphere knows that it flares, blinks, and seems to pulse with life. And you can imagine those priests standing in the blue-grey of early morning, watching the star's sharp, shimmering dance over the desert, and taking its flicker not only as a herald of water, but as a trembling boundary between human order and the caprice of the Nile. In their precise temple art, Egyptian stars are drawn as five-pointed flowers, idealized and calm, yet the reality confronting the priests on those crucial mornings was closer to a living flame, always on the verge of vanishing in the dawn glare, and their yearly anticipation gave the twinkling of Sirius ritual weight. If ever the star seemed unusually unsteady or coloured, it might hint at disturbances among the gods, so that even subtle variations in its glitter fed back into the cycle of festivals, offerings, and royal proclamations that organised Egyptian life. Far to the east, in ancient China, court astronomers climbed wooden towers to read the sky on behalf of the emperor, whose mandate from heaven needed constant affirmation, and in the dense, meticulous records of the Han dynasty, you see evidence of a different style of attention. Stars are described as sparkling like dew, flashing many colours, trembling like candle flames in the wind, and while these phrases appear in a context of portents, alongside cometary tails and guest stars, now known as supernovae, they also testify to an empirical sensibility, a recognition that stars do not present themselves as static points, but as restless, occasionally iridescent sparks, whose behaviour correlates with weather, season, and direction in the sky. Chinese observers noticed that stars low in the southern sky or near the horizon shimmered more violently, and they associated such vibrating lights with unstable qi in the air, blending philosophical notions of vital breath with careful watching of atmospheric conditions. Over centuries, they correlated unusual flickering with halos around the moon, or with coloured rings around the sun, building a kind of early climatology of optical phenomena in which each agitated star was both a sign from heaven and an index of what the surrounding air was doing far above the fields. Now shift to the shores of the Aegean, where Greek thinkers began to wrest the sky away from myth and give it to geometry and reason. Yet even for them there remained the stubborn fact that some celestial lights waver while others shine smoothly. Aristotle, whose influence on later centuries would be immense, confronted this in his treatise Meteorologica, where he writes that stars seem to tremble because their light passes through the turbid exhalations of the sublunar region, a realm of vapours, smoke, and ever-changing air, whereas the planets, he claimed, do not twinkle as much because they are closer, and their light has less of this disturbed medium to traverse. For Aristotle, the universe is divided into a perfect, immutable realm beyond the moon, and an imperfect, changeable region below it, and the flickering of starlight becomes a piece of evidence in that grand architecture. Stars belong to the divine, uncorrupted ether, but their appearance to our eyes is contaminated by the restless air in which we live. The steadier light of the planets, which wander, or planen, against the fixed star background, hints at their hybrid nature, closer to us and therefore less subject to the optical distortions that plague the most distant fires. Aristotle's explanation is wrong in its details. We now know stars are not all equidistant on a crystalline sphere, and planets are not physically closer by a factor that would sharply reduce twinkling, but his instinct that the atmosphere is the culprit marks an essential step, because it shifts the blame from the heavens themselves to the medium in between, and he supports this claim with analogies a listener in his time would understand. Just as a torch seen through smoke appears to dance and change shape, so the star seen through the moist, heated exhalations rising from Earth appears to jitter and flash. A few generations later, Hipparchus and then Claudius Ptolemy took Greek skywatching to new levels of precision, and in Ptolemy's monumental Almagest, you encounter the first systematic scale of stellar brightness, the 6 magnitudes that still structure our catalogues today. Although he did not yet possess a theory of why brightness fluctuates moment to moment, his careful descriptions of stars as bright, faint, or flickering show a sensitivity to how atmospheric conditions change the apparent intensity of light, and in a separate work, his Optics, he studied refraction by passing light through water and glass, noting how objects seen through thick media appear displaced and distorted, an insight that quietly supports Aristotle's notion but adds an experimental dimension. In Optics, Ptolemy highlighted how the bending of light increases as the angle of incidence grows, a fact anyone can verify by looking at a straw in a cup and seeing its broken appearance, and he then extended this to celestial phenomena. Stars low on the horizon, seen through a thicker cross-section of air, should appear not only displaced upward, but also more subject to the shimmering caused by unequal densities in that air, and although he did not use the language of density gradients or temperature inversions, his tables of refraction corrections for different altitudes are early quantitative attempts to tame, with numbers, the same processes that make stars flicker. While Greek and Hellenistic thinkers elaborated such theories, ancient India developed its own astronomical tradition, expressed first in Vedic hymns, and then in more technical texts like the Vedanga Jyotisha and the later Siddhantas, where the heavens are treated as both sacred and calculable, and within that literature appear scattered remarks about the trembling of stars, especially those rising or setting, which were thought to be filtered through vapours associated with the monsoon or with seasonal changes, linking optical effects to a broader rhythm of water, wind, and divine order. Indian sky watchers, particularly in the classical Gupta period, were keenly interested in planetary motions for astrological and calendrical reasons, and they knew from naked eye practice that, unlike the sharp, quivering pinpricks of distant stars, the planets generally maintained a steadier gleam, a sensory distinction they incorporated into their classification schemes long before anyone could articulate why an object's apparent angular size should matter to how it responds to atmospheric turbulence. To them, the difference contributed to the metaphysical distinction between the wandering grahas and the more remote fixed nakshatras that marked lunar mansions. As Greek works found their way into the Arabic-speaking world after the rise of Islam, the question of why stars twinkle while planets mostly do not reach scholars in Baghdad, Basra and Cairo, where the House of Wisdom became a crucible for translating, critiquing and extending classical knowledge. There, under caliphal patronage, astronomers like Al-Faghani, Al-Battani and Ibn Yunus refined Ptolemaic models, while physicists and philosophers began to pull apart Aristotle's blended notions of exhalations and ether. Among them, the most important for our story is Ibn al-Haytham, known in the Latin West as Al-Hazan, who around the year 1021 completed his Kitab al-Manazir, the Book of Optics, a masterpiece that did more to change how we think about light and vision than any work since antiquity, and within it he addresses not only reflection and refraction, but the way apparent sizes and shapes of celestial bodies change with viewing conditions, insisting on experiment, passing light through glass spheres, through layers of heated and cooled air, and noting how point-like sources can appear to blur, stretch or quiver when the medium is unstable. Ibn al-Haytham argued forcefully against the then common belief that rays emanate from the eye toward objects. Instead, he maintained that light travels from luminous bodies to the eye in straight lines through a transparent medium, and that any irregularity in that medium alters the path, so that the apparent trembling of stars arises from the ceaseless, microscopic bending of their rays by layers of air at different temperatures, densities and motions, a view strikingly close to the modern one, even if he lacked the later mathematics of waves and turbulence to fully formalize it. This emphasis on the medium opened a door for later Islamic scholars, such as Qutb al-Din al-Shirazi and Kamal al-Din al-Farisi, who explored atmospheric optics in the context of rainbows and halos, studying how light can be split into colours or scattered, and in their discussions of halos around stars and planets, one perceives an awareness that the same inhomogeneous air causing those rings and arcs also agitates starlight. The sky is no longer a smooth dome but a dynamic lens with endlessly shifting patches of refractive power. When Ibn al-Haytham's work was translated into Latin in the 12th and 13th centuries, it entered a European milieu still dominated by Aristotle, but increasingly receptive to measurement and natural philosophy, and scholastic thinkers in Paris, Oxford and Bologna took up the puzzle of twinkling in a new way, sometimes treating it as a moral allegory, the unstable star symbolizing the fickle soul, while also proposing physical causes such as vapours and smoky exhalations shimmering in the air between Earth and the celestial spheres. One medieval commentator, Roger Bacon, drawing heavily on Alhazen, speculated that the same cause that makes the sun appear flattened at the horizon, refraction through denser air, must also be responsible for the irregular sparkling of stars, and he suggested experiments with candles observed through glass flasks sometimes filled with hot water and sometimes with cold, to demonstrate how changing the medium's state affects the apparent steadiness of the flame. In these crude setups, long before lasers and precision optics, you see the first laboratory analogues of stellar scintillation, recreated on a table in a dark monastic cell. Meanwhile, far from libraries and disputations, seafarers along the coasts of the Mediterranean and in the Indian Ocean were learning that the twinkle of stars held practical information, because the roughness of the sea and the clarity of the air could be judged by how violently certain familiar stars quivered, and a skilled navigator looking up from a tossing deck at a bright star near the horizon could sense from its rapid, chaotic flicker whether there were high-altitude winds or incoming weather systems invisible to any other instrument of the time. During the great voyages of the Age of Discovery, when Portuguese and Spanish caravels pushed into the Atlantic and beyond, captains and pilots combined newly printed star charts with a more ancient embodied skill, reading how stars behaved rather than how they simply were, and logs from the 15th and 16th centuries sometimes note that stars near the equator burn with troubled light, or sparkle most violently on humid nights. Observations that, when stripped of their metaphors, testify to the sensitivity of mariners to how warm, moist air in tropical regions intensifies the bending and scattering of starlight. As Europe entered the Renaissance, the invention of the telescope in the early 17th century suddenly interfered with this age-old experience of a glittering sky. Because when Galileo Galilei turned his crude but revolutionary instrument toward bright stars, he discovered something paradoxical. The twinkle that dominated the naked eye view diminished significantly, and stars, though still small, appeared as tiny disks or blobs of more or less constant brightness, while Jupiter's moons and the planets showed crisp, stable shapes most of the time, strongly reinforcing the emerging idea that whatever made stars flicker belonged not to them but to the atmospheric corridor between the object and the observer. Galileo did not know that the little disks he saw were not true sizes of stars but diffraction patterns imposed by the finite aperture of his telescope. Yet his realization that magnification tamed twinkling fundamentally altered how astronomers thought of the heavens, because it separated the sensory appearance of stars into two realms: the raw, unstable sparkle experienced by poets and travellers under open skies, and the more disciplined, even light accessible to those who peered through tubes of glass and metal, effectively putting star twinkling on the list of things to be corrected or bypassed in the pursuit of cosmic truth. At almost the same time, Johannes Kepler, serving as imperial mathematician in Prague, dug deeply into refraction in his work Paralipomena to Vitello, using it to explain why the sun and moon look larger at the horizon, and his geometrical treatment of light bending through layers of air with changing density pointed directly toward a more accurate theory of how a stratified atmosphere refracts starlight into deflected paths that vary over time. Though he focused on large-scale displacement rather than rapid flicker, the conceptual move from a simple uniform atmosphere to a vertically structured, gradient-filled one gave later thinkers tools to model the continuous jostling of rays that produces twinkling. In the decades that followed, light itself came under new scrutiny, and competing theories arose. René Descartes and later Isaac Newton favoured corpuscles, tiny particles travelling in straight lines and bouncing or bending at boundaries, while Christian Huygens elaborated a wave theory in which light spreads as disturbance in an all-pervading ether. Both camps, in different ways, were forced to reckon with phenomena like rainbows, halos, mirages, and stellar scintillation, because any adequate description of light had to account not just for straight-line travel, but for the complex ways in which real media, glass, water, air, alter its course. Newton's experiments with prisms in the late 17th century showed definitively that white light is a composite of colours of different refrangibility. And when you realise that each colour bends at a slightly different angle when it passes from one medium to another, a fresh detail appears in the night. The subtle flashes of red, green and blue around a twinkling star, especially near the horizon, are not illusions but the result of atmospheric refraction, acting more strongly on some wavelengths than others, so that as turbulent cells of air with varying temperature and density pass in front of the starlight, they disperse its colours unevenly, turning the star into a miniature fluctuating prism. Even without formal wave theory, 18th century astronomers began to notice that different nights had different qualities of air, which they called seeing, long before that term acquired a rigorous definition. In observatories like those in Paris, Greenwich, and Königsberg, careful record keepers like Cassini, Flamsteed, and later Bessel noted how on some nights star images in their refractors appeared sharp and motionless, while on others they boiled, danced, and flickered so badly that precise measurements of position and brightness became nearly impossible, forcing them to classify nights by their steadiness and correlate that with wind, temperature, and time of year. Such pragmatic attentiveness intersected with a growing quantitative understanding of atmospheric refraction, driven in part by the need to correct navigational tables for sailors. As astronomers like Bradley and Maskelyne refined the laws relating a star's observed altitude to its true position above the horizon, they treated the atmosphere as a layered medium whose density decreases with height, using barometer readings and temperature profiles to fit empirical formulas that could predict the overall bending of light, and in doing so they set the stage for recognizing that irregularities, departures from the smooth gradient, must be responsible for the residual rapid fluctuations we experience as twinkling. The 19th century brought a revolution in optics because the work of Young, Fresnel and others finally established light as a wave phenomenon, which meant that the bending and distortion caused by the atmosphere could be treated not only as ray deflection, but as the interference of phase-shifted wavefronts, rippled and corrugated by each pocket of warmer or cooler air they crossed. George Biddle Airy, in his 1835 analysis of diffraction through a circular aperture, gave the world the Airy disk, the theoretical image of a point source formed by a perfect, aberration-free telescope. And soon after, careful observers realized that the shimmering and flickering they saw in star images were deviations from this ideal caused by the constantly evolving pattern of turbulence in the air above the instrument. When the Scottish physicist Lord Rayleigh investigated scattering and the colour of the sky, he had to confront how air molecules and small particles scatter different wavelengths of light differently, giving us the blue of daytime and the reddening of the sun at sunset. And though his work focused more on diffuse scattering than on refraction, it provided the mathematical machinery, scaling laws, dependence on wavelength, that later researchers would adapt to describe how small-scale fluctuations in refractive index along a light path produce intensity variations at the observer, the formal name for which became scintillation. At the same time, meteorology itself transformed from a collection of descriptive practices into a physics of fluids, and Lewis Fry Richardson's early 20th century attempts to describe turbulent flow with differential equations, later synthesized by Andrei Kolmogorov, gave a statistical picture of turbulence as a cascade of eddies of many sizes, from large atmospheric waves hundreds of meters across down to tiny swirls gliding on millimeter scales, all of which can modulate density and thus the refractive index of air, so that a star's light, crossing this restless multi-scale stew, accumulates a constantly changing patchwork of phase delays that, when finally projected onto your retina or a telescope's focal plane, appear as flickering. Laboratory physicists, curious whether such scintillation could be mimicked indoors, began to pass coherent beams of light, eventually lasers, through heated air columns, turbulent water tanks, or rotating glass plates with varying thickness, and they observed directly how initially smooth intensity patterns broke up into speckles, fringes, and rapidly shifting bright and dark spots, offering a controlled analogue of stellar twinkling and confirming that it arises not from intrinsic changes in the star but from interference and focusing effects imposed by a randomly varying optical medium between source and observer. Astronomers, now equipped with sensitive photographic plates by the late 19th and early 20th centuries, discovered a curious consolation. While the eye integrates light over mere tens of milliseconds, making it exquisitely sensitive to rapid brightness fluctuations, long exposure photographs tend to average out twinkling, so that stars recorded on plates appear as nearly uniform dots, even on relatively poor seeing nights, allowing the slow accumulation of data on star positions and magnitudes that would have been impossible with visual methods alone. For them, twinkling became something to outrun with longer exposures rather than something to decipher in real time. Yet for those who persisted with visual observing, double star enthusiasts, variable star watchers, and planetary observers, twinkling remained a constant companion, its behaviour an exquisite gauge of atmospheric steadiness. On nights when bright stars near the zenith shivered only gently and their colours stayed constant, one could push telescopes to higher magnifications, resolving close binary systems or fine belts on Jupiter, whereas on nights when even high-altitude stars sparkled violently and their images in the eyepiece boiled, the atmosphere was said to be in bad humour, a poetic acknowledgement that the same processes responsible for twinkling also limit the ultimate resolving power of ground-based optics. It was in the mid-20th century that the connection between twinkling and image quality crystallized into precise mathematics. Fried and others, who introduced parameters like the Fried coherence length, R0, a measure of the size of a telescope aperture over which atmospheric turbulence can be considered roughly uniform. If your telescope's diameter is smaller than R0, the atmosphere behaves like a single, gently moving lens, and the star image, though perhaps wandering slightly, remains sharp and relatively stable. But if your aperture exceeds a size 0, different parts of it see different phase distortions, and the resulting interference produces a dancing, smeared image, essentially an enlarged, time-varying manifestation of the same fluctuations that, to the naked eye, appear as twinkling. This quantitative understanding fed directly into the choice of sites for major observatories. By the 1960s and 70s, astronomers scoured the globe for mountaintops with thin, laminar airflows and minimal local turbulence, placing telescopes in places like Mauna Kea in Hawaii, La Silla and later Cerro Paranal in Chile, and the Canary Islands, where the atmosphere above is often remarkably stable, reducing both twinkling and image blur, and they measured seeing, not poetically but numerically, in arc-seconds of point spread function width, using scintillation monitors and differential image motion monitors that transformed the once mystical shiver of starlight into a dataset to be plotted and compared. Throughout this evolution of theory and practice, a simple, observable contrast continued to intrigue both casual and professional sky watchers. Stars twinkle, but planets usually do not, or at least far less. And the reason lies not in some metaphysical difference, but in geometry and coherence. Because a star at astronomical distances is effectively a point source, with its light arriving at Earth as nearly parallel rays from an angular area too tiny to resolve, whereas a planet, being much closer and having a measurable disk even in small telescopes, subtends a larger angle on the sky, effectively providing many slightly different ray bundles that, as they pass through the same turbulent cells of air, are averaged together in your eye or detector, smoothing out rapid intensity fluctuations. When you look at Mars or Venus low on the horizon and notice perhaps a slight trembling or a soft blur rather than a sharp, flashing glitter, you are witnessing this averaging in action. The same pockets of warm and cool air that would cause a point-like star to flare or vanish momentarily instead modulate different parts of the planet's disk differently. And because your eye integrates over the whole, apparent brightness variations cancel out, leaving only a kind of shimmering of the planet's edges or a slow, wavy distortion of its shape, distinct from the abrupt high-frequency twinkling of stars nearby. Closer to the horizon, however, even planets can seem to flash or ripple, because the light must traverse a thicker wedge of atmosphere filled with more extreme gradients of temperature and density, and under these circumstances the distinction between extended and point sources blurs somewhat. Still, the rule holds. The more the source covers many independent turbulence cells in the sky, the less dramatic the net scintillation, which is why satellites with their tiny angular size can occasionally scintillate like stars, while the broad diffuse glow of a nebula or galaxy appears steady, even though its photons suffer the same underlying distortions. For the everyday observer, colour is another clue. Bright stars like Sirius, Capella or Betelgeuse often flash between spectral hues when near the horizon, appearing alternately red, green, blue or white, an effect intensified on nights of strong temperature contrast between ground and upper air, and this chromatic twinkling made such stars figures of fascination long before the physics was known. Poets across cultures compared them to gems rotating in the heavens, or to eyes winking with many-coloured tears, capturing with metaphor what we now explain as dispersion, by layers of air acting momentarily as tiny prisms, splitting and recombining the star's light so rapidly that the eye fuses the sequence into a shifting jewel. Artists, too, responded to this restless quality of starlight, perhaps none more famously than Vincent van Gogh, whose painting The Starry Night from 1889 portrays the sky over Saint-Rémy as a riot of swirling, turbulent strokes, the stars surrounded by concentric halos and spirals of colour. Modern analyses by physicists and art historians have shown that the statistical properties of those brushstrokes resemble the patterns seen in turbulent fluids described by Kolmogorov, suggesting that Van Gogh's depiction of starlight and sky captured, intuitively and emotionally, something fundamentally true about the dynamic medium between us and the stars, even though he knew nothing of refractive index structure functions or scintillation indices. As the 20th century progressed and rockets began to pierce the atmosphere, carrying instruments above the turbulent layers for moments or minutes at a time, A new possibility emerged: to escape twinkling entirely by placing telescopes in space, beyond the distorting reach of air. And when the Hubble Space Telescope was launched in 1990 and finally brought into focus after shuttle-serviced repairs, astronomers marvelled at its ability to produce exquisitely sharp, diffraction-limited images of stars that did not flicker, revealing the universe in a clarity no ground-based instrument, no matter how large, could match without some method of undoing the atmosphere's mischief. Yet even as space telescopes offered this pristine view, engineers and physicists on the ground were developing a remarkably audacious technique to fight twinkling directly: adaptive optics, which uses deformable mirrors, wavefront sensors, and high-speed computers to measure the instantaneous distortions imposed by the atmosphere on starlight, and then push and pull the mirror surface in real time, hundreds or thousands of times per second, to cancel those distortions, effectively flattening the corrugated wavefront and restoring a star's image to its ideal airy disk, as if the telescope were floating above the atmosphere rather than buried beneath it. To make adaptive optics work, astronomers needed bright reference points in the sky, guide stars, near their targets. But because nature does not always provide one, they learned to create artificial stars by firing powerful lasers into the upper atmosphere, exciting sodium atoms left by meteor trails some 90 kilometers high, so they fluoresce as bright point-like beacons. By analysing how these man-made stars twinkle, the system infers the turbulence along the line of sight and corrects for it, turning twinkling from an obstacle into a diagnostic tool, a constantly updated fingerprint of the atmosphere's structure. Under the quiet hum of servo motors and cooling systems at observatories like Keck, the Very Large Telescope or Subaru, adaptive optics has restored to Earth-based telescopes a clarity once thought reserved for space, enabling them to resolve disks of distant stars, image exoplanets nestled close to their suns, and map the motions of stars swirling around the supermassive black hole at the centre of our galaxy. And all of this depends on reading and counteracting the same tiny, capricious shifts in refractive index that your naked eye experiences as the gentle, romantic twinkling of a winter sky. Beyond visible light, twinkling appears in new guises. Radio astronomers studying signals from quasars and pulsars discovered scintillation in their data as well, caused not by Earth's lower atmosphere but by irregularities in the ionosphere, and even in the tenuous interstellar medium, where clumps of plasma act as lenses that focus or defocus radio waves. In this broader context, scintillation becomes a universal phenomenon of wave propagation through random media, linking the flicker of a star seen by a shepherd to the fluctuations of a pulsar's signal received by a giant dish antenna. Historically, humanity's interpretation of twinkling has mirrored its shifting relationship to the cosmos. For the Babylonians and Egyptians, it was a divine code. For the Greeks and medieval scholastics, a clue to the structure of the spheres and the nature of the sublunar air. For Renaissance and early modern scientists, a nuisance that blurred precise measurements. For 19th and 20th century astronomers, both an obstacle and a source of insight into atmospheric physics. And for contemporary astrophysicists, paradoxically, a thing to be both cancelled technologically and studied as a probe of the very medium they seek to look through and beyond. Today, if you step outside on a clear night and look up with this history in mind, the simple question, why do stars twinkle, opens into a layered answer. Because every beam of starlight that reaches you has crossed an ocean of moving air whose temperature, density, and wind patterns constantly fluctuate in eddies and waves. Because light, as a wave, is exquisitely sensitive to such fluctuations, acquiring wrinkles in its phase that, upon interference at your eye or detector, become rapid brightness and colour changes. Because stars, unlike planets, are so distant and compact that these fluctuations are not averaged out, but stand in sharp, restless relief. And because for tens of thousands of years, humans have watched this delicate, shimmering instability and woven from it myths, navigation techniques, experiments, and technologies, turning an ephemeral sparkle into one of the most enduring connections between the shifting air of our small world and the unchanging fires that lie far beyond it. Yet even with all of that in mind, when you stand under a night sky and feel your gaze pulled toward a star that will not hold still, you're still only seeing half the story, because the rest of it unfolds not in the atmosphere but inside your own eyes and brain. where pulses of light are translated into electrical signals and then decoded by neural circuits whose quirks help determine how raw, physical scintillation becomes the lived experience of twinkling. In the dim conditions of night, your vision shifts from cone-dominated, colour-sensitive photopic mode to rod-dominated scotopic mode, and those rods, more numerous but less discriminating, respond sluggishly and with a certain amount of noise, so that tiny rapid fluctuations in light intensity arriving from a star are not merely recorded but filtered, amplified, or even created by the probabilistic way photoreceptor cells release neurotransmitters, which means that some fraction of what you call twinkling is a dialogue between external turbulence and the inherent graininess of biological detection. In the 19th century, physiologists and psychophysicists such as Hermann von Helmholtz and Gustav Fechner began probing the thresholds at which the human eye can distinguish flicker, using carefully controlled light sources modulated at different frequencies, and they discovered what is now called the flicker fusion threshold. Above a certain rate, roughly 50-60 flashes per second under bright conditions and lower in dim light, discrete flickers blur into the perception of steady illumination, implying that if stellar scintillation occurs faster than your rods and cones can respond, you will simply perceive an averaged brightness, whereas slower or irregular oscillations stand out as genuine twinkling. This frequency sensitivity helps explain why some people, especially children with fresh, unadapted eyes, report more conspicuous twinkling than older observers do, and why the effect appears different when you avert your gaze slightly so the star falls on a more rod-rich part of the retina. Ancient sky watchers could not have named photoreceptors or temporal integration, but in the way they spoke of stars that dance at the edge of sight, you can feel an intuitive awareness that the periphery of vision, where rods dominate, experiences stellar unsteadiness more acutely than the foveal centre. Because of this physiological filtering, the border between physical scintillation and psychological illusion can be porous, and in the 20th century, researchers in visual perception devised patterns like the scintillating grid, illusion, an arrangement of white dots at the intersections of grey lines on a black field, where ghostly dark spots seem to flash in and out of existence, that reveal how the brain constructs, and sometimes invents, twinkling-like phenomena from static stimuli, suggesting that some part of the star's vibrato quality might be supplied by your nervous system trying to make sense of sparse, noisy, high-contrast input in the dark. While scientists dissected perception in the laboratory, traditional cultures that lived much closer to the unpolluted night had long since woven the behaviour of starlight into practical knowledge systems, and among the master navigators of the Pacific, the Polynesian wayfinders who crossed thousands of kilometres of open ocean in double-hulled canoes, the sky was not merely a map of positions but a living report of conditions, where the steadiness or agitation of certain guiding stars could hint at upper-level winds, high clouds invisible at sea level, or the presence of moist, unstable air associated with storms. In the oral teachings preserved in places like the Caroline Islands, Micronesian navigators learned star paths, rising and setting points for dozens of stars along the horizon, but they also paid attention to the quality of their light. A star that glittered sharply and changed colour near the horizon might indicate turbulent, moisture-laden air, which, combined with the feel of the swells and the sound of the wind, offered subtle but crucial information about weather systems over the empty ocean, information that could mean the difference between a safe landfall and a disastrous encounter with typhoons. In northern Australia, many Aboriginal groups embedded atmospheric effects into their star lore as well, recognising that stars appearing to shiver more intensely often preceded strong winds or changing seasons. Among the Wardaman people, for instance, twinkling can be read as a sign that the spirits are cooking the air, signalling hot conditions to come, and while such language is mythic rather than technical, behind it lies a careful empirical correlation between scintillation and the onset of convective turbulence as the land heats or cools. In the Arctic, Inuit hunters travelling over sea ice at night also noticed differences in the behaviour of stars when warm air from the south intruded, or when temperature inversions formed near the surface, leading to phenomena like looming, where objects appear elevated, and to changes in the sharpness and stability of stellar points. In that environment, where subtle cues could signal dangerous thinning of ice or the approach of storms, an eye attuned to how stars flicker or blur was an essential instrument, as important as a modern barometer. These indigenous ways of knowing atmosphere through the sky parallel, in a different idiom, the work of modern atmospheric physicists who learned to use scintillation not just as a nuisance, but as a remote sensing tool, measuring how rapidly and strongly stars fluctuate to reconstruct the vertical distribution of turbulence above a site. Techniques such as SAIDAR, scintillation detection and ranging, split a star's light in a telescope and analyse the pattern of scintillation across the pupil, allowing researchers to infer where in the atmosphere, at what altitudes and with what strength disturbances are most pronounced. By repeatedly applying SIDAR and related methods like SLODAR and mass-dim at potential observatory sites, scientists have built up detailed climatologies of turbulence, finding, for example, that some mountaintops are afflicted by a persistent roiling boundary layer, a few hundred meters thick, while others lie under more benign, laminar flows, and these subtle differences can make the contrast between average seeing of 1 arcsecond and of half that, a small number on paper, but the difference between a blurred point and a sharply defined star in a large telescope, which in turn affects whether twinkling is fierce or subdued when seen from that mountaintop. As global climate patterns shift, with changing jet streams, altered temperature gradients, and more frequent extreme weather events, a new question has begun to stir among astronomers and atmospheric scientists. Will the characteristic twinkling of stars as averaged over years and decades change as well, not in the immediate sense of one night's bad seeing, but statistically, as the structure of turbulence in the lower and middle atmosphere evolves? And although the answer is not yet clear, long-term archives of seeing measurements and scintillation indices may one day serve as records of how planetary scale changes trickle down into the tiniest shivers of starlight. For those who briefly escape the atmosphere altogether, the contrast is so stark that it becomes a kind of revelation when US astronaut John Glenn orbited Earth in 1962 aboard Friendship 7. He reported that the stars he saw through the spacecraft window were steady and piercing, lacking the familiar twinkling, an impression echoed by later astronauts on Apollo and by crew members on the International Space Station, who often remark that from orbit stars simply burn with unwavering intensity, rising and setting behind the curved limb of Earth without any restless flicker, except in those fleeting moments when their light grazes the upper atmosphere and acquires a brief, shimmering edge. In those reports lies one of the most direct experiential confirmations of what centuries of theory implied. Remove the veil of air, and the stars do not twinkle, they blaze, and the only remaining unsteadiness comes from your own vehicle's tiny vibrations, or from micrometeoroid impacts on the station's structure, not from any cosmic volatility in the luminous points themselves, underscoring with visceral force that twinkling is an earthbound experience, a signature of living under a deep dynamic atmosphere. If you imagine standing on the surface of another world, however, the story might be strikingly different. Picture yourself at dusk on Mars, where the sky's not blue but a dusty butterscotch hue, and where the atmosphere is thin, only about 1% of Earth's surface pressure, but composed mostly of carbon dioxide and often laden with fine particles of dust that can loft high into the air, and you might ask whether stars seen from there would twinkle more or less than they do from a terrestrial desert. The lower density of Martian air means there is less material overall to refract and scatter starlight, which would tend to reduce scintillation, but the steep temperature gradients near the surface, as the ground readily cools or warms radiatively, can drive strong convection and turbulence in the boundary layer, while dust, with its complex scattering properties, adds another layer of optical irregularity. As a result, a Martian observer might find that stars overhead, far from local turbulence, appeared relatively stable, while those near the horizon, shining through long paths of dust-filled, thermally stratified air, flickered with a more erratic ochre-tinted sparkle than the familiar blue-tinted twinkling seen from Earth's moist nitrogen-oxygen air. On Titan, Saturn's large moon, the story would shift again. There, a thick atmosphere rich in nitrogen and hydrocarbons wraps the surface in a deep haze, turning visible light into a diffuse glow that barely penetrates to the ground. any stargazer standing on Titan, eyes peering through amber clouds, would likely see no stars at all, only a dim monochrome sky, so that the very possibility of twinkling would vanish, not because there is no turbulence, but because the medium is so optically thick and scattering-dominated that point sources are erased before their subtle intensity fluctuations can reach an observer. The diversity of twinkling, or its absence, across worlds is mirrored conceptually in astrophysics, where the term scintillation has been generalized to describe intensity fluctuations in many wavebands and environments. Radio astronomers speak of ionospheric scintillation, caused by irregularities in the charged upper layers of Earth's atmosphere, of interplanetary scintillation, as radio waves from compact sources like quasars and pulsars pass through the turbulent solar wind, and of interstellar scintillation, as radiation traverses clumpy plasma between stars, and in each case the essential idea remains the same, even as the scale and medium change. In the early 1960s, at the Mullard Radio Astronomy Observatory near Cambridge, Anthony Hewish and his colleagues exploited interplanetary scintillation to study the solar wind, aiming fixed radio antennas at distant compact radio sources and watching how their intensities fluctuated as the turbulent plasma streaming from the sun swept across the line of sight. By analysing these variations, they could infer the speed and structure of the solar wind long before in situ spacecraft measurements were available, using a kind of radio twinkling as a probe of an invisible tenuous medium filling the solar system. It was within this experimental context that Jocelyn Bell, a postgraduate student analysing miles of chart recorder paper from Hewish's array, noticed a peculiar highly regular scruff in the data, signals that pulsed with astonishing regularity about once every 1.3 seconds, which, after careful elimination of terrestrial interference and satellites, turned out to be the first discovered pulsar, a rapidly rotating neutron star whose beamed radio emissions swept across Earth like a lighthouse, although the pulsations themselves were intrinsic to the source and not a form of scintillation. Their detailed shape and intensity still bore the imprint of propagation through the interstellar medium, meaning that even in the discovery of one of the most exotic celestial objects, the principle of waves modulated by a random medium played a quiet background role. Back in the optical regime, another subtle branch of inquiry emerged in the mid-20th century that used fluctuations in light intensity in a creative way. The work of Robert Hanbury Brown and Richard Twiss on intensity interferometry, originally devised in the 1950s to measure the angular diameter of bright stars by correlating the arrival times of photons at two separate telescopes, a method that does not rely on conventional imaging but on statistical correlations in the fluctuating light stream. Their experiments, which involved measuring the tiny, rapid variations in intensity at two stations separated by up to hundreds of meters, and computing how correlated those variations were as a function of separation, allowed them to deduce the size of stars like Sirius, and in doing so they stumbled into the quantum nature of light, sparking debates about photon bunching and coherence that ricocheted through both astronomy and quantum optics. In a sense, they were reading a refined, engineered form of twinkling. Not the gross scintillation imposed by the atmosphere, which they minimized by working at short separations and with bright sources, but the microscopic intrinsic fluctuations of light itself. Modern optical astronomers, in their quest to detect exoplanets via the tiny dips in stellar brightness, caused, when a planet transits across its star, have had to confront and meticulously mitigate twinkling, because scintillation from our atmosphere introduces noise that can easily swamp the 1% or smaller brightness decrement caused by an Earth-sized planet crossing a sun-like star. To beat down this noise, they defocus their telescopes slightly to spread the starlight over more pixels, average over many comparison stars in the same field, and choose sites and times with exceptionally low atmospheric variability, employing statistical techniques to distinguish true periodic transit signatures from the stochastic flicker imposed by turbulence. Ground-based transit surveys like WASP, HatNet, and others have successfully discovered hundreds of exoplanets despite this handicap, yet the ultimate precision in transit photometry came from space telescopes like CoRoT, Kepler, and TESS, whose instruments orbit above the atmosphere and therefore above scintillation, allowing them to detect fractional brightness changes of tens of parts per million. Subtle, slow twinkles, caused not by our air but by the passage of distant worlds, by star spots rotating in and out of view, or by stellar oscillations that cause a star to rhythmically swell and contract. These space-based light curves, measured over months and years, reveal a different kind of celestial variability than the high-frequency sparkle of twinkling. They show that stars are not perfectly steady furnaces, but living, vibrating spheres whose surfaces shimmer with granulation and convective cells, whose interiors ring with acoustic modes, and whose magnetic fields pepper their photospheres with dark spots and bright faculae. In them you discover that beyond the quick, atmospheric jitter visible to your unaided eyes lies a slower, more intrinsic symphony of brightness changes, one that ancient observers could not resolve but sometimes intuited when certain stars subtly brightened or faded over months or years. Even at shorter timescales, some stars truly flicker on their own, independent of any medium, as in the case of cataclysmic variables and accreting white dwarfs, where unstable flows of gas from a companion star produce rapid, quasi-random light variations nicknamed flickering, a term that sounds almost domestic but in fact refers to chaotic processes near incredibly dense compact objects. Distinguishing this intrinsic astrophysical flickering from the extrinsic atmospheric twinkling requires careful observation and modelling, but outside of professional observatories, high-speed digital cameras now allow dedicated amateurs to record scintillation in ways that were previously impossible, by capturing thousands of frames per second of bright stars and then analysing frame-to-frame variations in intensity and shape. They can actually visualise the speckle patterns produced by atmospheric turbulence, those shimmering mosaics of bright and dark spots that dance across the detector as eddies of different refractive index slide past. From such datasets, one can compute scintillation indices, structure functions, and even infer wind speeds at different altitudes, turning a backyard telescope into a crude but informative turbulence profiler. This democratization of measurement echoes, in a modern, technical key, the long human tradition of reading the sky's unsteadiness for practical ends, and it finds parallel applications in fields as diverse as laser communication, where engineers must predict and compensate for scintillation when sending narrow beams of light through the atmosphere to satellites or aircraft, and power grid management, where rapid fluctuations in received light at solar farms under broken cloud fields can cause micro-variations in output that must be buffered, all instances where the interplay between coherent beams and turbulent media produces something very much like twinkling, just at less romantic wavelengths. From the cockpit of a commercial airliner cruising at 11 kilometers above sea level, a pilot looking down at the night side of Earth sees a different sort of twinkling. The lights of cities and towns passing through patches of thin cloud, haze, and turbulent temperature inversions can flicker and scintillate in ways literature has long seized upon this signature as a metaphor, perhaps because twinkling, more than the steady radiance of planets or the diffused glow of the Milky Way, suggests uncertainty, vulnerability, and the interplay of constancy and change. In Shakespeare's plays, stars that give a faint unequal twinkle often mirror a character's wobbling fortune or wavering resolve, while in Japanese haiku, a single trembling star glimpsed through moving branches or heat haze can evoke the fragile transience of life, the way even distant, seemingly eternal things appear to quiver when seen through the lens of human experience. Romantic-era poets, walking under industrializing skies where coal smoke and city lights began to dull the stars, often wrote nostalgically of the twinkling heavens of their youth, and in their laments you hear not just anxiety about progress, but a recognition, however imprecise, that the quality of the night's unsteadiness had changed. The sharp flicker of starlight was being replaced by the steady yellow glare of gas lamps, then electric bulbs, whose own slight scintillation at mains frequency was too fast to notice, so that the living capricious sky was gradually supplanted by a man-made firmament of uniform, controllable brightness. As light pollution has spread over the last century, swallowing faint stars and washing out the Milky Way for billions of people, the visible experience of twinkling has retreated into rural pockets and designated dark sky reserves, where perhaps a child taken camping for the first time stands under a truly dark night and feels an almost ancestral astonishment at the number and behaviour of the stars. For that child, unaware of turbulent spectra or refractive index structure constants, the question, why do they twinkle, may fall from their lips with the same mixture of wonder and need that once moved a Babylonian scribe to press a stylus into wet clay and record that some star, on some night,